Thank you, Matti, for the introduction. President, ladies and gentlemen. Actually, I think I rewrote the title in another, or reordered the title. I'll be talking about antimatter materials and some nuclear stuff as well, somehow entangled. Where should I stand? Maybe here. So anyway, I'll start with the basic question in material physics, or one of the fundamental questions, which is why is matter what it is, and how it is, and so on. And since I'm a materials physicist, not a particle physicist, I'll be stating the same thing as Mika Sillanpää just some time ago, that matter is made of atoms. If you're a particle physicist, you'll start talking about what atoms are made of and so on, but not going to that now. And just to give you an idea of what are the scales here, atoms are formed of protons and neutrons in the nucleus. And then there's a cloud of electrons. It doesn't really look like that. There's more like a blob of electrons around the nucleus. The thing in the middle, made of protons and neutrons, is about 10 femtometers in size. Can't really see that. The size of the atom, on the other hand, or essentially defined now by the cloud of electrons, is a bit bigger. The unit is called 1 angstrom. It's 0.1 nanometers, or if you wish, a lot of zeros and 1. The main difference between these two scales, I mean, the 1 angstrom and the nucleus size, is that this is actually accessible by modern microscopes. You can see individual atoms nowadays, but not the nucleus. Okay, so we're talking about fairly small things, as pointed out already in the previous talk. Now looking at it a bit from the chemistry side of things, if you wish, this is something you tend to see in a chemistry class, this periodic table of elements. You have different kinds of atoms. Not all the atoms are the same. And the atoms, how they differ is, or the main thing is the amount of protons in the nucleus, and followed then by the number of electrons in the electron cloud. Then depending on the number, then you have different atoms called hydrogen, helium, so on, and they have very different properties. I'll be focusing in the next few minutes, on a particular subset of these materials to illustrate a couple of things. And these two materials come from this part of the periodic table. There's possibly one of the most important elements of the modern era, silicon. Every single one of you probably has a device either on your hand or in your pocket that contains some silicon. It will contain other elements as well. But then those of you who are friends of Blu-ray discs, or PlayStation 3 or 4, or any future devices, you will be liking a lot gallium nitride. That's another material. It's a compound material now. It's not just made of one element. It's gallium and nitrogen. Also, if you want to put LED lighting or general lighting made out of LEDs at your home, you will have gallium nitride at your home. So this is the second most important material of our era, or possibly even the most important. Before I continue, I'll let you touch these materials a bit. Since I'll be talking a bit about the structure, you can pass it around, and at least my 3D perception is a bit limited, so it's easier if you can see the things or touch the things in your hand and see the three-dimensional structure. So luckily it seems that the colors here on the slides are the same as in real life. Gallium atoms are red, nitrogen atoms are green, silicon atoms are black. So atoms in these materials, for example, like silicon or gallium nitride, they are in this sort of periodic structure. They are nicely packed into a very ordered, you call it crystalline lattice, with the interatomic distances being about 5 times the size of the atoms themselves, roughly speaking. So the scale is correct, just blown up a bit. Just to tell you how the density of these things, you have about 10 to the 23 atoms per cubic centimeter. Cubic centimeter is the size of the end of your little finger, if you have big fingers. Silicon is something that you could also call the world's purest material. It can be manufactured with a purity which is better than 1 to the power of 10 to the 12th. So you have less than 1 in a, what is it? 10 to the 12th is, in English you call it a trillion. And these are structured somewhat like this. Okay, so now you've been passing those around, you have maybe an idea what it looks like, then just imagine squeezing it by 8 orders of magnitude, and then you're inside a crystal lattice. Now, why is this important? Essentially all the properties of materials, at least, are dictated by the identities of the atoms that form them and in how these atoms are packed into this sort of structure. So not only the identities, but also sort of the positions of the atoms matter in matter. Properties that they influence, of course, you can imagine tons of properties. They can be, you can think of electrical properties, whether the material that you have made out of these atoms conducts electricity, whether it conducts electricity always or just in certain conditions. And of course, then you can ask yourself that why does it do so? The same goes for optical properties. You can have, well, these two are seemingly similar. Also, if you look at those things that are going around, you see that each atom is surrounded by 4 other atoms close by. However, silicon, if you have it in your hands now for real, it's kind of this, looks like gravel. It's like this grayish stuff. Gallium nitride, on the other hand, if you take it in your hand, if you have a big piece of it, it looks like glass. It's transparent optically, colorless. So optical properties. Why do they look like what they look like? And of course, are the other properties then of the material affected by exposure to light? Then again, this list can be continued. Thermal properties, mechanical properties, all the properties are defined or determined by the identities of the atoms and the structure they're in. So perfect materials are kind of boring because their properties are what they are, and that's it. However, the nice thing about materials like silicon and gallium nitride is that even if you make very little changes to the atomic structure, say that in silicon you replace 1 in a billion silicon atoms by something else, really just 1 in a billion, and you completely change the properties of this material. Suddenly it goes from insulating to conducting electricity. You can tune it, you can do a lot of different things to its optical properties, in particular in the case of gallium nitride, and this is kind of miraculous. And you can do this really by very simple changes. You can do it by replacing 1 in a billion atoms by something else. In silicon, for example, you put a phosphorus atom instead of silicon atom, or 1 billionth of them. You can have atoms in this sort of 3D structure that has been passing around. You can have atoms in the wrong place. Again, it's enough to have 1 in a billion of atoms in the wrong place, and the properties change. You can have atoms missing. In a position where you should have an atom, there's no atom. I like these guys. And you can have, of course, you can imagine all sorts of combinations of these things. Or more extended defects, bigger things, But I'm interested in these small things. And as I said, starting even from very small or low concentrations, you start changing the material properties a lot. But then the question comes that how do you know what's going to happen when you don't do this particular change? That's a good question, actually. And the opposite question as well. You see a property of this material. How do you know what's giving you this particular property in this particular sample? Before going into that, just reminding you that scales of things, you had something like this in your hands. We're talking about 0.1 nanometer scales. If you go to, and of course, the actual materials used are not just that much of atoms, but then much bigger, like on the millimeter scale or micrometer scale, which means many, many more atoms. If you look at organic molecules, they tend to have features on a much larger scale than what I showed just here. And then if you take actual components, say in optoelectronics, they can be on the tens of nanometers up to micron scales. For example, the spot that emits light, if you have an LED light bulb in your house, is not very big actually. And all what's happening inside is defined by things on this scale or atomic scale. So, how to figure out what the structure of a given material is? Physicists, what they like to do, or what we like to do, is we take a piece of the material, we call it a sample, and then we shoot something at it and see what comes out. The short version. That's a typical way of telling what things are. You can shoot electrons, you can shoot other atoms into it, you call it ion beam methods. You can shoot radiation at the sample, and then what you see that comes out, it can be again electrons that are coming out, you can see radiation coming out, you can see atoms coming out of the sample, and trying to identify what was it that made these things come out when we shoot this thing in. So you have electron microscopes, you have ion beam methods, magnetic resonances, and all these tell you about something about the very little details about the atomic scale structures in this sort of a material. You can look at it from the other way, other direction, asking yourself, what are the properties of these materials? So you can, if you're interested in optical and electrical properties, you can look at shooting light at the sample, looking at what sort of light come out, and trying to understand what could have caused this particular change in, say, the wavelength of light. Or electrical properties, how resistive the samples are, how much charge they have inside, making this sort of a certain kind of capacitance, for example. So you measure the properties, and then you try to understand the atomic scale phenomena that take place. That usually then requires, of course, some theoretical insight that I'm not going to discuss now. So what are the challenges in this? Can we know everything about the atomic structure in a given material? If you're given a piece of material, can we find out what there is inside, what it looks like inside? Well, the answer is yes and no. The electron microscopes, especially transmission electron microscopes, the modern ones, they can take images of samples that look, say, like this. You can see individual atoms. This looks like just the black thingy that was going around looked at from the side. So you can actually see individual atoms. You see that you have some parts in this particular sample that doesn't look as nice and ordered as the silicon. And then there's another section here. So these are really I would say, the flagships of atomic structure studies of materials. However, there's a problem. If you take the smallest defects where you have atoms missing or extra atoms, they are very hard to find with this method. Especially, you can think of one problem right away when you look at this picture. If you have 1 in a billion atoms that's different, you need to take quite a few pictures to find one. That's not going to happen unless you have unlimited time for your PhD. Another problem is that you have to prepare the samples in some way in order to get this sort of picture. And that's prone to actually create these one atom defects. So you don't know whether if you see a defect, that sort of a defect there, you don't know whether you made it by preparing your sample for the experiment or whether it was there already. So even though this is really the nicest thing you can imagine, it has some limitations in a subset of these defects, which actually happen to be very important for many properties. Then you have other methods like the magnetic resonance methods I mentioned, but they have limitations on what sort of samples you can measure, all sorts of limitations, although they give very detailed information about the point defects that we were missing in this kind of experiment. But you have to have sufficiently thick samples or sufficiently resistive samples, or you have to have enough of these defects to find them. You can think of ion beam methods that are very sensitive to impurities, or impurities now meaning that you have wrong atoms in the lattice, or improper atoms in the lattice. But again, it requires kind of high concentrations. In our work, we focus on one method that actually brings a possibility for studying a certain type of point defects in particular, which is the vacancy defects or the missing atoms that I said I loved just a few slides ago. So positron annihilation spectroscopy. This is the antimatter part. The positron is an antiparticle of electron. It has the same mass but opposite charge. When it meets an electron, they annihilate each other and produce strong gamma radiation. You can get positrons in a very complicated way by taking a nuclear reactor or a big accelerator or a free electron laser and using pair production as a source for positrons. Or you can do it the way we do it. We just go and buy some table salt where part of the sodium has been replaced by sodium-22, a radioactive isotope of sodium, and it produces positrons. That's a very neat way. And in matter, if you put a positron inside this sort of crystalline lattice, the positrons will want to go where the atoms are not. So they like to be in between the atoms. And if you remove one atom from the lattice, the positron, which is the gray blob here, likes to localize itself into this part where there was no atoms. And by studying the radiation that comes out, we can actually tell what atoms were missing, how many atoms are missing, what is the density of these sort of defects. And we can combine this with all sorts of electrical, optical properties. We can also shine light on the samples at the same time. And you can do all sorts of studies where you identify and quantify those particular kinds of point defects that positrons see. To do that, we use, for example, these sorts of positron accelerators, which have been built here on campus. There's a few of them in Nanotalo across the street. And, well, they are not big accelerators. They're kind of small. It's a few meters, not very big. You can fit it into a lab, a smallish lab. And just as an example, physicists, in addition to liking to show oscillations, the other thing physicists like to show is decays. So this is now an example of what the experimental data we obtain might look like. So this is number of annihilations as a function of time. So this represents somehow the lifetime of the positrons inside the crystalline sample. We measure how much the positron actually likes to stay there before it's annihilated with the electrons. And if you have these vacancy type defects or missing atoms, this lifetime becomes longer and longer, and you can, using that as one of the quantities, you can tell how big the vacancy defects in question are. And just as a fun example, what we have done with this is that we've, for example, shown where the smoky brown color of the purest diamonds comes from, and it happens to come from these big vacancy clusters. And you can tell that by looking at the experimental positron lifetime as a function of shining light on the samples during the experiments and at the absorption measured in these particular samples. And then you can remove this by all sorts of thermal treatments, and you can nicely correlate everything, and you find out finally that this piece of diamond is brown because of these vacancy clusters, as an example. So, what about nuclear engineering? That's the one word I haven't said anything about yet. So I've been explaining how these material studies work, what we want to find out, how we do it, and the main take-home message from that, I'd say, is that matter can be studied using antimatter. Positrons are antimatter. Defects in the semiconductor-like materials, silicon, gallium nitride, diamond, you can, by understanding and controlling them, what you can then contribute to is to making better electronics, new components. However, what we use are methods from nuclear engineering. We're doing fast gamma ray spectroscopy. We're measuring quite strong nuclear radiation, in fact. So this is the link to nuclear engineering, if someone was wondering. The other link in the research and teaching is that what we also do is understanding radiation damage in solids. Radiation causes damage in these atomic structures. And you can try to understand that and how it's formed and what it takes to build up into bigger damage that eventually cracks the material or makes the mechanical properties suffer so much that they can no longer be used in a nuclear power plant. There's a big potential problem, especially when plant lifetimes for nuclear power plants are getting longer and longer. At some point, you have to know how much radiation a particular part can take before it breaks down. So it's an important thing for nuclear safety to understand radiation damage. And that's it. Thank you very much. Take-home messages.